Hi everyone, my name is Mert Aydın. Today I will briefly describe my project, which is Photonic crystal optical structure design in 4 current applications. This project is supervised by Professor Dr. Çiğdem Seçkingürel. In this project, we want to design one-dimensional photonic crystal for current studies. You may ask, what is photonic crystal? Photonic crystals are composed of periodic dielectric, metallodielectric, or even superconductor microstructures or nanostructures that affect electromagnetic wave propagation in the same way that the periodic potential in a semiconductor crystal affects electrons. By defining allowed and forbidden electronic energy bands, photonic crystals contain regularly repeating regions of high and low dielectric constants. In this project, we started with wide literature research. We made our own preliminary design by looking at past studies. Generally, we use transfer matrix method for analyzing photonic crystal structures. The transfer matrix method is based on the fact that, according to Maxwell's equations, there are simple continuity conditions for the electric field across boundaries from one medium to the next. If the field is known at the beginning of layer, the field at the end of the layer can be derived from simple matrix operation. A stack of layers can then be represented as a system matrix, which is the product of the individual layer matrices. The final step of the method involves converting the system matrix back into reflection and transmission coefficients. In photonic crystal design, generally people are using different types of series. For example, true Morse, Fibonacci, and Cantor series. In this design, we preferred 9th step of Fibonacci series. After that, we add some defection to our Fibonacci series for improving the performance of filter. Our defection was chosen in periodic structure. One of the important points in our design is material properties. We choose 3 different materials, which are tellurium, silicium dioxide, potassium niobide, and we choose thicknesses 175 for all materials. Let's look at our design. Now we are looking reflectance versus wavelength. As you can see, our design behaves like perfect reflector, nearly between 475 and 1330 nanometer. When we look transmittance in same interval, our design transmits 0 signal. Finally, if we look power absorbance graphs, since we didn't use any metallic material, we observed almost 0 power absorbance. Conclusion: this structure is perfect reflector, visible range and near infrared region. This photonic crystal can be used to reflect some specific wavelengths and filter other wavelengths in imaging and laser systems. Thanks for listening.